Hi, so you're going through the PAT paper from 2012, going through parts A to C of question 22. Question 22 is an exceptionally difficult question and it has to be thought about very carefully. So we're told that a point object of mass 1 kilogram is placed at the point x0 equals 10 meters at rest. It then moves according to this force here, F, that depends on displacement. So in part A, we're asked, what is the speed of the object at x equals 0 meters? Well, okay, so we know it's moving along the x-axis under some force. And we have here a force versus distance graph. So we know that the area underneath this graph is force times distance. Force times distance, is work done. So force times distance will be the area under the graph will be the work done on the particle. And that will be equal to its change in kinetic energy. So we know that half mv squared, its final kinetic energy at x equals 0, is equal to Fx. Well, what force does it move under? It moves under a force of 10 newtons for a distance of 10 meters. So that's equal to 10 times 10, or 100 joules. Well, we know its mass is 1 kilogram, and therefore v squared is equal to 200, where therefore velocity is the square root of 200, or 14 meters per second, to two significant figures. Okay, so now where it starts to get tricky. So part B says to sketch its kinetic energy as a function of x. So I'll start by drawing the axes down here. Okay, so let's start with the first bit over on the right-hand side of 0, the positive region. This is where the force is constant. So we know the work done on the object is actually constant as he moves from 0 to 10. There's no increase in work done. It's done exactly the same amount. And therefore, the increase in kinetic energy is going to be linear with distance. And we know that it reaches a kinetic energy of 100 joules at the point x equals 0. So we have 100 joules here, and we know it's going to be a linear increase from x equals 10 to 100. Okay, so now what happens? Because now we have the particle acting under a force that is increasing from negative to positive. So first of all, let's think about what actually is happening here. So along here, we have the particle moving at some velocity in the negative x direction, and it's going to keep accelerating in the negative x direction as the force, because the force is still negative, so it's still accelerating, up to here. But at this point here, the force suddenly changes to a positive force acting in the right hand, the positive direction. So in fact, as our particle is moving in the left-hand direction, it's going to be decelerating and continually decelerating up to a point where the work done by this force is equal to the work that was done here and accelerating it. So there's going to be a point where the kinetic energy is actually 0. Now what's that point going to be? Well, that's going to be when the work done here on the particle is equal to the work done up to some value here of x. Okay, so what is the work done? What's the area under the graph? So the area under the graph here was 100. So we want 100 plus, well, this is 10 by 10 over 2, so that's 50, to be equal to, well, we need the area of this. Well, let's just say it has some maximum force here. And this will be the force that we want to find, what we use to find the area. So how do we find out what the force corresponds to and the x corresponds to? Well, let's just say it's going to be equal to some force F times some distance x over 2. So Fx is going to be equal to 300. And we're going to use that to find x. Okay, so how are we going to find that? Well, we know that there's also going to be, if there's going to be a 0, there's going to be a maximum. So when is there going to be a maximum point of kinetic energy? Well, think about this logically. It's as we said before, it's still increasing, accelerating in the negative direction. And even though the force is decreasing, it's still acting on it in the same direction. So it's still accelerating right up to the point here where the force changes direction. So the maximum velocity is going to correspond to the point where x is equal to minus 10. So it's going to be a maximum at the point x is minus 10 here. So we're going to have some kinetic energy maximum. Well, as the increase is now linear, we're actually going to have it being a curved shape. And the reason for that, well, the reason for that is probably a complicated reasoning that we won't bother to go into, but the way we can deduce it is that we know it must reach a maximum, and we know the relationship was linear when the force was constant. So if we presume that we have, imagine you have y equals x squared, y equals x cubed. We have a constant term here corresponding to a linear term, y equals x. And then we have a not constant term, a y equals x term here. So that will correspond to a y equals x squared term here. So it's going to curve to a maximum. So we're going to have this curving up to some maximum value here at x is minus 10. Now, what is this maximum value? Well, the maximum kinetic energy is going to be equal to, well, we've worked it out. It's the area underneath here, which is 150 joules. So we know it's going to have a maximum here at 150 joules. And then, well, it's going to be the same like quadratic relationship. It's still going to curve, but it's going to curve down, and it's going to meet a 0 at some point here. But how are we going to work out what that point is? That point x. Well, the way we're going to do that is we know that the area above here now must be equal to 150, must be equal to the maximum, the total amount of work done here. Okay. But we know that the gradient of this line is 1 because it moves from across 10 and up 10. So we know that this value of x here will be the same numerically as this value of f. So in fact, we get from here that x squared is equal to 300 joules. And so x is equal to the square root of 300, which is approximately equal to 17.3. But then we see that in fact our x-coordinate wasn't the distance from here to here, it was distance from here to here. So in fact it's going to strike at 10 more than this, or minus 27.3. So this here is minus 27.3. And that is our graph of kinetic energy versus distance. Okay, so we've now been asked to work out, to sketch the velocity and acceleration again as functions of time, not of distance this time. Okay, so how are we going to find our relationships with time? Well, we know that we have points where our acceleration is constant and where it is not constant. So for this region here, in fact what we'll do is we'll start by labeling the region. So we'll call this region A, this region B, and this region C. So let's consider region A. Well, we have a constant acceleration, so we can use our Suvat equations. We know it moves in the x direction by minus 10, and we know it starts at a velocity of 0. We know it reaches the point 0 is the velocity of minus 14. We worked that out in part A. And we know A is minus 10. So how long is it in there for? Well, we know V is equal to U plus AT. And therefore, minus 14 is equal to minus 10t. And therefore, it's here for 1.4 seconds. What about in region B? Well, we know it reaches there with a speed of 14 meters per second. If we take the modulus of it. And we know that it leaves there with a maximum speed of 17.3. We worked that out from the fact that our maximum kinetic energy was 150 joules, and that corresponded to a speed of 17.3 meters per second. Okay, well, we know that the gradient here is 1. And so that means that the force increases at a constant rate. So what we can do is we can take an average of what the force is. So we can average that the force is between 0 and minus 10. And so average it out as a force of minus 5 newtons. And as we know the mass of the object is 1 kilogram, this means that the acceleration, A, is going to be equal to 5 meters per second to the minus 2. And therefore, well, we know that acceleration times time will be the change in velocity. So AT is equal to delta V. Well, AT is 5t. We want that to be equal to the change in velocity. Well, that's 3.3. And this tells us that t is equal to 0.64 seconds. So it's in the section B for 0.64 seconds. And similarly for C. Well, it enters C at 17.3. And we know it's going to leave C, well, stop in C at V is 0. Again, we know A is equal to 5 meters per second to the minus 2. So we get that, in fact, sorry, that shouldn't be 5 meters per second. That should be the average of the force within this section. And that was corresponding up here, remember, to a force of 17.3 newtons. Make that a bit neater. 17.3 newtons. And so we average it as half 17.3 newtons. Okay, well therefore we see that A is 17.3 over 2 meters per second, and therefore 17.3 over 2t is equal to the change in velocity, well that's 17.3. And therefore we see it's in section C for 2 seconds. It comes to the end of section C after 2 seconds. Okay, well now we can sketch our graph for acceleration. So let's do that. Make it a bit longer, so like this. Okay, well, this is A meters per second minus 2 and t measured in seconds. So we know it's going to have a value at minus 10 because that's the acceleration within region A. We know it's going to leave region A at a time of 1.4 seconds. And we know it's going to leave region B at a time of 1.4 plus 0.64, which is 2 seconds. Okay, well we know it's going to take 2 seconds to get from here to the end, and similarly 2 seconds to get from here back. So we're going to have a point at 4 where it reaches the end, and a point at 6 where it comes back out of C. Then we get 6 add 0.6, 6.6, where it leaves B, and finally we get a time of 8 seconds where it comes to the end of A. So let's draw that. Well, we know in section A the acceleration is constant. So we're going to have a constant line down here at 10. It's then going to increase up to 2 seconds and then come to a maximum here. So basically what this means is as it gets to when it actually stops instantaneously at the end of C, it's actually accelerating its largest amount. So it accelerates its largest amount at 4 seconds, where it comes to the end of section C, and it comes back down, and then comes into section B, here. It then leaves section B down here, and it has a constant acceleration of minus 10 meters per second up to time is 8 seconds. So that's acceleration versus time. Okay, now, so for velocity versus time. So let's just sketch that out. We're going to have the same regions of 1.4, 2, 4, 6, 6.6, and 8. So this is time and velocity. Now just remember roughly what our graph looked like for A. So it was flat here, and then came up to a maximum and came back down like this. Now, the way we're going to do this question is we're going to think about what we know about acceleration and velocity. Well, we know that acceleration is the time derivative of velocity. So what that means is this graph, at every point, it's going to correspond to the gradient of this graph. So we have here, up to 1.4, that the gradient is constant. And we know that it's negative. So that means that we're going to accelerate linearly downwards in a straight line up to 1.4 seconds. We then get a negative gradient, but increasing, becoming less negative, up to the point here where the gradient is going to be 0, because this corresponds to A equals 0 or dV by dt equals 0. So we're going to have a stationary point here. And we know that this point here corresponds to 2 seconds. So we're going to have a stationary point at 2 seconds. So we're going to come down like so, and have a stationary point here at 2 seconds. The gradient's then going to increase but become more positive, but at a changing rate. So they come like this, and then we notice that it's going to be a maximum at the time t equals 4. So that corresponds to this maximum point here. It's then going to become, still remain positive, but become less positive, less positive, less positive until it's 0. So we have a stationary point here again, and that's going to correspond to 6 seconds. So it's going to come up like this, and have a stationary point at 6 seconds. And then it's going to, as before, have a negative gradient in this section, and then a straight period. So have a negative gradient up to 6.6, and then continue linearly down from 6.6 to 8. So it's going to have a maximum of 6, come down like this, and then decrease linearly down to 8. So that is our velocity versus time graph.